The frequency of the wave determines the pitch. The frequency of an audible sound wave determines how high or how low we perceive the sound to be, which is known as pitch. As the frequency of a sound wave increases, the pitch rises. The frequency of a wave is an objective quantity that can be measured, while pitch refers to how different frequencies are perceived by the human ear. Here I have 3 glasses of water, each filled with a different amount of water. Because I don't have a frequency meter that determines the exact frequency, we are going to determine which glass has the highest frequency by determining the pitch. So whichever glass has the highest pitch also has the highest frequency. So here we can conclude that the glass with the least amount of water has the highest pitch, so it also has the highest frequency. Another type of sound wave is called an ultrasonic wave. These waves can produce images. Ultrasonic waves have short wavelengths, and because of this, they have widespread medical applications. For example, these ultrasonic waves can produce images inside the body. This is possible because sound waves are partially reflected when they reach a boundary between two materials of different densities. In order for ultrasonic waves to see an object inside the body, the wavelengths must be about the same size or smaller than the object. The most common application of ultrasonic waves is to observe fetuses. This picture gives a better understanding of how ultrasonic waves are used to observe a fetus. The speed of sound depends on the medium. Sound waves can travel through solids, liquids, and gases. Because waves consist of particle vibrations, the speed of a wave depends on how quickly one particle can transfer its motion to another particle. For example, solid particles respond more rapidly to disturbance than gas particles do because the molecules of a solid are closer together than those of a gas are. As a result, the sound waves generally travel faster through solids than through gases. The speed of sound also depends on the temperature of the medium. As the temperature rises, the particles of a gas collide more frequently. Thus, in a gas, the disturbance can spread faster at higher temperatures than at lower temperatures. In liquids and solids, the particles are close enough together that the difference due to temperature changes is less noticeable. Sound waves travel away from a vibrating source in all 3 dimensions. Spherical waves can be represented graphically in 2 dimensions with a series of circles surrounding the source. So let's say this black dot is our source. These 3 circles represent compressions, otherwise known as wavefronts. Each circle represents a spherical area. The distance between adjacent wavefronts is equal to 1 wavelength. Now these are radial lines, otherwise known as rays. These represent the direction of motion. This is called the sine curve. Each wavefront corresponds to a crest of the sine curve, which in turn corresponds to a single ray. This is a 2-dimensional representation on how sound waves travel away from a vibrating source. Now let's talk about the Doppler effect. The Doppler effect is a frequency shift that is the result of a relative motion between the source of waves and an observer. So let's demonstrate this. I'm going to bring my music closer to me, and it will get louder and I will hear a higher pitch. But when I bring my music closer to you, you will hear it louder and it will be a higher pitch to you, and to me it will be a lower pitch and it will be a lot softer. There was a huge difference between when it was right next to my ear and when it was a couple feet away from me. So this represents a frequency. Now we'll talk about sound wave intensity. Intensity is the rate of energy flow through a given area. The equation for the intensity of a spherical wave is intensity equals power divided by 4 pi times distance from the source squared. This equation shows that the intensity of a sound wave decreases as the distance from the source increases. This occurs because the same amount of energy is spread over a larger area. Intensity and frequency determine which sounds are audible. The frequency of a sound wave heard by the average human ranges from 20 to 20,000 Hz. The loudest sounds that the human ear can tolerate has an intensity of about 1 watt per meter squared. This is known as the threshold of pain. Now you're going to hear several different noises that have different frequencies all the way from 1 to 20,000 Hz. This is 1 Hz, 10 Hz, 50 Hz, 100 Hz, 150 Hz, 200 Hz, 300 Hz, 500 Hz, 700 Hz, 1000 Hz, 1500 Hz, 2000 Hz, 3000 Hz, 4000 Hz, 8000 Hz, 10,000 Hz, 15,000 Hz, and 20,000 Hz. Now let's talk about resonance. Resonance is a condition that exists when the frequency of a force applied to a system matches the natural frequency of vibration of the system. A great example of this was when the Tacoma Narrows Bridge in Washington was set in motion by the wind. High winds set up standing waves in the bridge, causing the bridge to oscillate at one of its natural frequencies. The amplitude of the vibrations increased until the bridge collapsed. Finally, we're going to briefly discuss harmonics. The fundamental frequency is the lowest frequency of vibration of a standing wave that is possible. Now, harmonics are integral multiples of the fundamental frequency. However, a harmonic series is a series of frequencies that includes the fundamental frequency and the integral multiples of the fundamental frequency. The equation for a harmonic series of standing waves on a vibrating string is frequency equals harmonic number times the speed of waves on the string divided by 2 times the length of the vibrating string. Standing waves can also be set up in a tube of air, like in brass instruments and woodwinds. While some waves travel down the tube, others reflect back upwards, and these waves combine to produce standing waves. If both ends of a pipe are open, all harmonics are present. The equation for this is frequency equals harmonic number times the speed of sound in the pipe divided by 2 times the length of the vibrating air column. If only one end of the pipe is closed, only odd harmonics are present, and the equation is the same except the 2 changes to a 4. The last thing we are going to discuss are beats. Beats are the interference of waves of slightly different frequencies traveling in the same direction and is perceived as a variation in loudness. The number of beats per second corresponds to the difference between frequencies. The average human ear can distinguish beats up to a frequency of approximately 10 beats per second. You hear sound every day, all the time, whether it's your phone ringing, the TV going, a person talking, a car driving by, or simply your feet walking on the floor. No matter where you go, you're always going to hear sound. Just not all of it's good. But I guess that's for you to decide.